Welcome to my presentation. My name is Tanisha Joshi, first year PhD student, currently working to evaluate the nature of dark energy using scalar fields. I'm going to present a talk titled The Astronomical Revolution LISA Connecting the Dots of Dark Universe. This talk is designed to make the audience familiar with LISA mission concept and clear their understanding in the best possible way. This presentation is structured as follows. Introduction. Why we use powerful instruments like Virgo, LIGO, etc. in the first place. What is LISA? Its scientific goals, model, how will it work in space? LISA Pathfinder. What was the utility of LISA Pathfinder? Gravitational waves. What are gravitational waves? Sources of gravitational waves. Connecting the dots. How the dots are connected by LISA. LISA is a probe of dark energy at all redshifts. That is, how LISA will be helpful in probing dark energy at all redshifts. And at last, the future prospects of LISA. Let's begin. There is a really exciting fact in cosmology that I can actually see the universe how it was in the past billion years ago. That is, the Big Bang, beginning, evolution, and structure of the universe. How? There is a fact in physics that light takes certain amount of time to travel from one place to another. For instance, if you are watching this presentation, light takes a fraction of seconds to reach your eyes, so you are going to see the presentation as it was fraction of seconds earlier, which imply if you are looking at objects farther and farther away, you are actually looking them right earlier in the earlier periods. In other words, if you look farther and farther away in the universe, you can actually see the universe as it was billion years ago. Through many kinds of telescopic structures, we are able to look at the universe. With the advent of new technologies, we have powerful instruments which can get us answers to some outstanding questions of the universe. One such powerful instrument is LISA. Let's talk about it. LISA, Laser Interferometer Space Antenna. The first question that comes to mind is why we need LISA when we have LIGO, which already had detected gravitational waves. We need LISA because LIGO reveals only a fraction of the waves we could observe. LISA will detect from a broader range of gravitational wave sources. Also, from space, LISA can avoid the noise from the Earth and can access regions that are inaccessible from Earth. It is a first space-based gravitational wave detector. It is planned to launch possibly around 2034 with a mission duration greater than or equal to 4 years. It is based on laser interferometry technique. It is sensitive to low frequency and has longer wavelength. That is, LISA can operate at a frequency range of 1 mHz to 1 Hz and can find waves with much longer wavelengths. Since gravitational wave signals are extremely small, so they require extremely high precision and high detection sensitivity. The scientific goal of LISA is to identify gravitational waves from gravitational wave sources and to use these measurements to further evaluate various astrophysical systems, cosmological theories, models, etc. LISA arrangement consists of three spacecrafts arranged in an equilateral triangle with three arms at a distance of 5 million kilometers. The distance between the satellites is precisely monitored to detect a passing gravitational wave. The entire arrangement is 10 times larger than the orbit of the Moon and will be placed along an Earth-like heliocentric orbit. Its three satellites form a giant Michelson interferometer in which two satellites act as reflectors and one satellite acts as source and observer. There will be free-falling test masses added inside the spacecraft using drag-free technology based on inertial sensors. As the gravitational wave passes through the interferometer, differential changes in the length of its arms will be sensed by laser interferometry. This is the basic model of LISA spacecraft. It will get refined and will get somewhat different after the addition of much needed new technology. This is the animated illustration of how LISA will work in space and detect gravitational waves. LISA Pathfinder. LISA Pathfinder is a test mission launched in 2015 and ended in July 18, 2017. It is basically sent to space to test the detector design. During its tenure of 2 years, it did not detect any gravitational wave. It exceeded its goal by a large margin by showing that the instruments sent to test the noise sensitivity were 5 times more accurate than actually hoped for. Gravitational waves. Gravitational waves are distortions, ripples in space-time fabric, first predicted by Einstein in 1915, caused due to the collision of massive orbiting objects like supermassive black holes, neutron stars, etc., act as a powerful new probe of the very early and late universe, first directly detected on September 14, 2015 by ground-based LIGO when two black holes merged. Gravitational wave sources. Gravitational wave sources are classified as supermassive black hole binaries, SMBHBs, intermediate black hole binaries, IMBHBs, extreme mass ratio and intermediate mass ratio spirals, EMRIs and IMRIs, stellar origin BH binaries, galactic binaries, stochastic backgrounds. This is the illustration of how gravitational waves are formed. These two neutron stars collide to give rise to gravitational waves, along with the burst of gamma rays that will get emitted just seconds after the gravitational waves. This is the first detected binary neutron star merger, GW170817. Connecting the dots. The dots, dark sector, new physics, quantum gravity, Big Bang are all connected by LISA through one common link, that is, gravitational waves. The dots stalked here are not limited to this only, they may increase or decrease according to one's perception. Let's talk about them. Dark sector. Dark sector comprise of dark energy and dark matter. For dark energy, at late times, LISA will probe the expansion with the standard sirens and will determine Hubble constant which describes the expansion rate of universe. For dark matter, LISA observations of rotating black holes could constrain or detect certain light bosonic fields that have been proposed as dark matter candidates. Quantum gravity. Gravitational wave signals from black holes could provide hints at quantum theory of gravity. New physics. At early times, LISA will probe the tera-electron volt or tera scale in early universe, which will lead to large extra dimension, thus solving hierarchy problem. Also, LISA will detect unexpected new exotic particles leading to new physics or physics beyond standard model. Big Bang. Black holes and galaxy mergers will play a vital role to decode the evolution, beginning and structure of universe as from the very beginning of structure formation. Black holes and galaxy mergers are an integral part of evolution of universe which grows over time through mergers and accretions. LISA will explore these black holes and galaxy mergers. LISA as dark energy probe at all redshifts. An important problem in present-day cosmology is the nature of dark energy. Dark energy is characterized by parameter W known as equation of state. LISA could play a vital role in investigating the physical origin of dark energy by treating gravitational wave sources as standard sirens. LISA could be used to measure equation of state W using the relationship between luminosity distance and redshift given as this equation. The above relation is derived assuming a flat FRLW universe and a time-independent W, and it depends sensitively on cosmological parameters, that is, Hubble constant, matter density parameter, and dark energy density parameter. Here W is time-independent. We can also derive it for time-dependent W. The luminosity distance will be given by the gravitational wave sources, whereas the redshift will be determined by its electromagnetic counterpart, which consists of optical, radio, X-rays, and gamma rays. Possible standard siren sources for LISA are MBHPs, SMBHPs, EMRIs. These three possible sources will probe the cosmic expansion from redshift equivalent to 0.01 to redshift equivalent to 10, which is really high as compared to supernova 1A, which gives redshift equivalent 1.5. Supernova 1A is a standard candle across cosmological distances to probe dark energy. In other words, adding other gravitational wave sources of LISA will improve cosmology at all redshifts. MBHPs map the expansion at high redshifts, which is useful to test alternative cosmological models. SMBHPs and EMRIs map the expansion at low redshifts, which is useful to test dark energy and constrain Hubble constant. Lower redshifts have no counterparts, whereas high redshifts have electromagnetic counterparts due to their gas-rich environments. Future prospects of LISA. LISA will be a giant step forward in observational cosmology and have a tremendous impact on many aspects of astronomy. LISA will give answers to some outstanding problems of astronomy as a whole, like does gravity travel at the speed of light? Does gravity couple to other dynamical fields like massless or massive scalars, and many more like that. LISA could always detect sources that nobody expected, so expect some surprising breakthrough discoveries. Once new results from LISA will be available, the relevance of certain topics will obviously change, which will add new sense to scientists' perception of universe. LISA's observational input will also be complementary to ground-based gravitational wave observations carried out by LIGO, Virgo, Kagra, etc. In summary, LISA has immense potential as well as bright prospects to unravel the mysterious universe, be it theoretically or observationally. That concludes my talk for now. Thank you for your time, patience, and attention. These are the sources I referred to while preparing the presentation.